Today we'll jump into a topic called matrices. Now, a matrix is defined as a rectangular array of numbers, as the slide states, and it's basically a whole bunch of numbers put into like a square set of brackets. Now, below is a actual matrix in this case, and these matrices have some notated positions, if you will. The dimension of a matrix is in a row by column form. So dimension, row by column. Now, if you look at the way these are notated, the 1 is the element in the first row, first column, the 5, first row, second column, the 3, first row, third column, -2, second row, first column, etc., 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 etc. So this is how we notate their positions in the matrix. Notice row by column here, and it basically is in line with what you see down below. Now, again, we talk about this row by column type of understanding of dimensions. And if we want to know the row by column here, we take the rows, which are like bleacher rows. So there's 4 of those here. Columns, like columns in the front of a big house, by 2. This is a 2 by 3. And this guy, 4 rows and 3 columns. Now, an augmented matrix is a matrix that basically describes the coefficients and solutions of a system of equations. So in this case, these are the coefficients and these are the solutions. Anything to the right of that little dotted line is a solution. So what this is replicating is 4x plus 8y equals 13, and -3x plus y is equal to 10. So you can probably guess what's coming up. We're going to use matrices to solve systems eventually, if not soon. Now, a couple of things we need to use to be able to do that is something called elementary row operations. And elementary row operations are operations done on a matrix that don't affect the solution of the system. So if we go back to the previous slide, when we solve this, we've done a lot of things. We could do a substitution, which is not going to be the case in this case, but we've also done multiplications, like multiply by 8 here, and then add these two, so on and so forth. And that kind of falls in line with these elementary row operations. So if you don't want to affect the system's outcome, you can do one of 3 things. You can switch 2 rows at any given time. You can multiply rows by a non-zero constant. And you can add 2 rows or multiple of 2 rows and replace that addition with another row. And I'll explain that in a couple of seconds. So row equivalent matrices are matrices that can be obtained from another by doing a simple row operation. So for instance, in this case, here's my original matrix, and this matrix right here is row equivalent because the new matrix is made by a multiple of 1/2 to the first row. So if again I go back, I've basically multiplied the first row by a non-zero constant, thus creating a new matrix that is row equivalent. Row echelon form. In order for a matrix to be in row echelon form, first of all, the rows can consist entirely of zeros, but they're going to occur at the bottom of the matrix. I didn't give you an example of one of those. The first entry in any row with a non-zero entry is 1. So you'll notice 1, non-zero entry, 1, 1. Likewise here, 1, 1, 1. And then the column subscript of the leading ones increases as the row subscript increases. So what that means is basically I'm moving over 1 each time. So you get a diagonal form, if you will, of 1s and then zeros below. Reduced row echelon form is basically like a row echelon form, except we've got that diagonal one that we previously talked about, and then zeros above and below each one that exists in the coefficient part of the matrix. So in this case, we're going to use something called Gaussian elimination to change this matrix into a row echelon matrix. And again, that row echelon matrix is going to look like diagonals of 1, 0 below the 1. Could have a number up here, and then on this side we could have 2 numbers. Okay, in so doing this, I can now say what the y value is equal to because I have that y variable isolated. Plug that back into my upper row and get my x variable. In order to make this happen, we're going to basically do row operations to this matrix to change it to this. To do so, I'm going to do the following. I'm going to rewrite my top row because that has exactly what I want in it. I have a 1 up in the upper left-hand corner. And what I want is I want to get a 0 down here. All right, so in order to get a 0 down here, if I were to take and add row 1 to -1/2 times row 2, that's going to get me a 0 right here. So watch how I do this. I multiply -1/2 by 2 and I get -1. -1 plus 1 is 0. To get from here down, I will multiply -1/2 by 3, which gets me 3/2. 3/2 plus 1 is 2.5, right? Or 5/2. And then lastly, I'm going to multiply -1/2 by 2, which is -1, add it to 6, which is 5. So this tells me what I've done and what becomes of it. Next, I want this number to be a 1. So the row operation I will choose to use, again, I'll leave the top the same because it has a 1 there. I want this to be a 1, so I'm going to take, and usually we substitute right here in R2, I'm going to take 2/5 row 2 and replace row 2 with that. So if I multiply 2/5 times 0 and replace it, I get 0. 2/5 times 5/2 gives me a 1. 2/5 times 5 gives me a 2. And now I am in row echelon form. I can say that y equals 2 because that's the only thing left right here. And I do know that x plus y equals 6 by what's left in my top row. Given that y is equal to 2, x plus 2 is equal to 6, and x equals 4. So in theory, I can say that I've solved that system using this process. And again, this is a process. It's not the most efficient way, but like I said, the process is eventually going to become important in later math, so we need to learn this now. Again, let's just practice it one more time just for kicks, and we'll do this with a 3x3 next for even more practice. So I write this down into its augmented matrix. Like so. Now you'll notice in this case, this is going to be a little dirtier because of the fact that I don't have any 1s in this. So let's go ahead and do this. I'm going to take, and I'll do it a little differently than I did last problem just to show you the flexibility you have in doing this. I'm going to take and multiply 1/7 by row 1 and replace row 1. And then I'm going to multiply -1/2 by row 2 and replace row 2. So in doing that, I get 1/7 here. I get -4/7 here. I get -3/7 here. And I get -1 here. And I just noticed a mistake, so I'm going to change that right now. When I multiply this by 1/7, I actually get 1. And then I multiply this, I get negative 5 halves. And in the last term, I get 7 halves. All right, now you'll notice I have my 1 where I want it, and I need a 0 right here. And I've set myself up to do this just by adding the two together. So next, I'm just going to take and do row 1 plus row 2 and replace row 2. So let's go ahead and do this. This adds very simply, but I'll keep row 1 as it is. And then row 2 is going to become a 0. And then we're going to add negative 4/7 and negative 5 halves, which is negative 43 over 14. You can do that on a calculator or do it manually if you'd like. And then I add negative 3/7 and 7 halves, and I get 43 over 14. How nice is that? Because what I want to do is I want to get a 1 right here. So in order to do that, notice all I have to do is multiply row 1 times negative 14 over 43. I lie this row 2 and replace row 2 with that. So row 1 remains the same. And row 2 becomes a 1 right here and a negative 1 right here. Therefore, I can say that y equals negative 1. I know that 1 minus 4/7 equals, and this is a 1x minus negative 4/7 y equals negative 3/7. Plugging negative 1 into here, I get x plus 4/7 is equal to negative 3/7. Bring that guy over and x equals negative 1. So a 3 by 3 is definitely going to be more work, and let's just go ahead and tackle one for example. In this case, fortunately, my first row has exactly what I need in it. So I'm just going to recopy that. I have my 1 in my upper left-hand corner. I need zeros down here. In order to do that, I'm going to multiply 2 of the negative type by row 1, add that to row 2, and replace row 2, and negative 3 times row 1 plus row 3, and replace with row 3. So in doing that, just got to go real careful, real slow. Negative 2 plus 2, 0. This is negative 4 plus negative 1 is negative 5. Negative 10 plus 1, negative 9. Positive 2 plus 2, 4. Bottom, negative 3 plus 3, 0. Negative 6 plus 4, negative 2. And negative 15 plus negative 4, negative 19. This does not look good. And then positive 3 plus 14 is positive 17. All right, so the bonus is we got the two zeros, and now we've got some ugly stuff to do next. So next, I'm just going to get my ones here, and I'm going to make this guy a positive 1 and this guy a negative 1. So I'll rewrite my first row again. I get 1, 2, 5, and a negative 1. I'm going to take and multiply negative 1/5 times row 2 and replace row 2. And negative, or I'll go actually positive 1/2 row 3, replace with row 3. Thus, I get 0, positive 1, 9/5, and negative 4/5. Row 3, I'm going to get a negative 1, a negative 19 over 5, and a 17 over 2. All right, the bonus of that was now I have 1 and negative 1 opposite each other, so I can add these two rows to get my 0 below that 1. So let's go ahead and do that. Copy row 1, and for that matter row 2, because they have what I need. Now I'm going to add row 2 to row 3, replace row 3. And adding these together, I get 0, 0. I take 9/5, add that to negative 19 over 2, gets me approximately, not approximately, exactly, negative 77 over 10. And fortunately, when I add these two together, I get 77 over 10. We're very happy because now if I want to get a 1 here, all I need to do, multiply by the reciprocal, so negative 10 over 77 times row 3, replace row 3. I'm going to copy the first two rows down. Like so. Do my multiplication. This fortunately goes to a 1. This becomes a negative 1. And then we go back and substitute. I'm not going to do the whole thing, but I basically have y plus 9/5 z is equal to negative 4/5. And I also have x plus 2y plus 5z equaling negative 1, and I know that z now is equal to negative 1. So I just do all my substitutions, first into here, and then I get my y and plug here, my z goes here, and I get my answer. And that about sums it up. Practice, practice. We'll see you next time.